Hi, my name is Naveen. I'm from ECB section bearing roll number 24BQ1A0496. Now I am discussing about the diode characteristics and I have mentioned that here I taken diode is PN junction diode. What is PN junction diode? Structure and function we have to know that first. A PN junction is a two-terminal semiconductor device that allows current flows from one direction only, that is forward bias, and it is formed by joining of the p-type semiconductor rich in holes and n-type semiconductor rich in electrons. First, we have to see in the diagram. This is a p-n junction. This is the n junction having number of holes, number of positive values. So the p-n junction have two two terminals which contains a rich in holes as p-type semiconductor and n-type semiconductor which is rich in electrons. Next, forming of p-n junction and diffusion and deflection region. In p-n junction diode, the forward bias. In p-n junction diode, there is a deflection region. Here, the diffusion of carries. When p-type and n-type materials are joined, electrons from the n-type diffuses into the p side, and holes from the one side diffuse to the n side. When the p-n junction diode is connected to a battery, then holes are moves towards the electrons and electron moves towards holes. The formation of ions. An electron leaves in n-type. We have to know that in n-type there are electrons. They have leave behind positively charged donor atoms. Similarly, holes leaving p side create negatively charged ion acceptor ions. So they are passes from each other to each other. Deflection region. In p-n junction diode, due to flowing of the electrons and the holes, the deflection region is formed between them. In forward bias, the deflection region is very thin. In reversal bias, the deflection region is increases, so the formation of the electrons does not possible. So p-n junction is only for only for forward bias. Here deflection region. These stationary ions for a region diode of a mobile charge carries known as deflection region or space charge. It is also called space charge region, which acts as insulator. Next, barrier potential. This is the deflection region. Barrier, let's discuss the barrier potential equilibrium state. The charge in the deflection region creates an electric field. Deflection region creates an electric field that passes further deflection of charge carries. The electric field establishes a potential difference across the junction called barrier potential. Here the electric field establishes a potential difference. Here the deflection region, here the electric field is positive and you have introduce an EMF. The EMF is induced means the electric field established. So the potential difference across the junction is happened. So barrier potential. Typically 0.7 for silicon and 0.3 for germanium here. An equilibrium, the diffusion current carries across the junction. Here at equilibrium, the diffusion of current carriers across the junction is balanced by the drift current due to electric field resulting in zero at net current. Next, forward bias. Overcoming the barrier. External voltage applied. A positive voltage source is applied to a PN side and negative source is connected to an N side, effectively reducing the barrier potential. For forward bias, we have to connect the positive terminal to an P type and negative terminal to an negative terminal to an N type side. Deflection region. The external voltage pushes majority carriers toward the junction, narrowing the deflection region, lowering the potential barrier. Here in previous we discussed that due to the flowing of the electrons and the holes, the deflection region is very decreases and so it is causes for the current flow. Current flows. Once external voltage exceeds the barrier potential, current flows exponentially through the diode. This is an on state. Next, reverse bias. In reverse bias, as we have to connect that positive terminal to an N-type and negative terminal to a P-type. We can just reverse the diode. Reverse the negative voltage. See, we have to in negative voltage applied P side and a positive voltage on N side. The configuration increases barrier potential and widens the deflection region. Here we can see that the deflection region increases between the p-type and n-type because of the reverse bias. So deflection region, the flow of electrons from the holes are So the flow of electrons are reduces. So the current does not conduct in this reversal bias. Majority carriers are pulled away from the junction. This does not deflection rate increases, so the electrons and holes are pulled away from each other. The widely deflection region acts as even stronger insulator. On a smaller leakage current, reverse saturation current flows primarily due to minority carriers. We have to see the KVA characteristics of the diode. Initially, it is at zero, and then and then it is current is increases by increasing the voltage. Next, reversal bias gene, and he also discussed about the reverse breakdown of gene or diode avalanche. In gene or we have see only the positive, only the negative, negative and positive. I think so. While diodes are registered to block diagram in reverse bias, applying a sufficient high reverse voltage can be lead to phenomena of reverse breakdown. Occurs in heavily doped electrons at lower level voltages. Avalanche breakdown. Zener breakdown only occurred heavily doped diodes at lower reverse voltages, but avalanche occurs a highly doped voltage at higher reverse voltages. And second point, due to stronger electric field across the narrow deflection, there is a deflection region between P and N. It's a process. It happens. Electrons are pulled from their atomic bonds. Minority carriers Minority carriers accelerate the strong electric field collide with the atoms and new electrons hole pairs. Current increases rapidly, but the voltage across the diode remains relatively constant. Current increases rapidly, but the voltage across, we can see the graph, means the graph is like at a zero, current increases, then the voltage is always constant at zero or one something else when the current is increases. But in avalanche background, the process cases leading to sudden and large increases in current. Voltage changes means the current also changes in large or small that like more affects it. Next topic. Diode models. We have to see different diode, ideal, practical, and complete. First, we have to discuss about the ideal diode model. Acts as perfect switch. Ideal diode is acts as perfect switch. Zero voltage drop in forward bias, infinite resistance in reverse bias, useful for quick and basic circuit analysis. Practical diode model includes a fixed voltage drop, example 0.7 for silicon and 0.3 for germanium in forward bias, and infinite resistance in reverse bias, more realistic for many applications. And third one is complete diode model. Consider the new voltage of bulk resistance in forward bias. The reverse saturation current provides accurate representation of the diode. So yes, these are the topics. And finally, we can know the key points taken from the applications of the diodes. If you know any item, then we have to know that how it is used in our life, in our daily life, and how to use it for the society, what is important. So here we discuss the diodes and we can see the applications of the junction diodes. Unidirectional conduction, the fundamental characteristics allowing current in one direction only. Yes, we have discussed that current flows in only forward bias for the PN junction diode. Barrier potential. The inherent voltage difference must be overcome the conduction. Bias condition. Forward bias enables current, reverse bias blocks. Key points that are this is not an application, it is in key points that what you will breakdown phenomenon. Zener and avalanche breakdown critical for specific diode types and circuit potential applications. We can see rectifiers for DC or AC to DC conversion, signal domination, voltage regulators, switching circuit, etc.